Hello. Today we will be talking about acids and bases and measuring their pH. Typically, or primarily, we will be talking about monoprotic acids and bases. So, what do I mean by monoprotic? Protic is mono, one, protic, meaning proton, so one proton. So, talking about acids that donate a single proton or bases that accept a single proton. So, strong acids. Strong acids are typically associated, or this is typically the title associated with acids that undergo 100% dissociation. Although this is typically true, it is not 100% true. Strong acids do mostly dissociate. However, there is a small portion that do not dissociate. For instance, let's look at the concentration of HCl, or not HCl, not the concentration, but rather the Ka. Ka is the acid dissociation constant. So that would be equal to 10 to the 10th to the 3.9. So big number. Let's see. HBr. Ka is equal to 10 to the 5.8. Hi. And to the 10.4. And maybe HNO3. These are more or less pretty big numbers, meaning that they undergo almost complete dissociation. For the primary purpose of things, we could, for instance, we are talking about an acid HCl. We could say that it is equivalent to concentration of H, or we could say it is equivalent to the concentration of. Just different ways of designating the acid in solution. So let's say we had 0.1 mole Cl. So this would give HCl plus H2O. Is in a reversible reaction, generating H3O plus Cl minus. We would say that the H is equal to negative log concentration of H3O. So if we punch this into a calculator, we get 1.00 for the pH. So this is using our typical means of calculations where we're using the concentration of strong acid and we're taking its concentration of pH formula. It's a concentration or a pH of 1.0. Let's actually now use a different approach for calculating a pH. This time we will be using activity coefficient 0.1 molar Cl. So in the same way, we have 0.1 molar Cl plus H2O. Act reversibly with H3O, Cl. If we are going to be using this activity coefficient, we need to find mu. Mu is equal to 1/2 the summation of the concentration multiplied by the charge squared. Put these values in. So C1 will be equal to the H3O. C2 will be equivalent to the Cl minus. And they will both be 0.1. Z1 is going to equal +1. Z2 is going to equal -2. And we just plug into the equation. So ionic strength of the solution will be equivalent to 1/2 C1, which is 1 multiplied by +1 squared plus 1 minus 1 squared equals 0.1 molar. We have a 0.1 molar concentration. If we go to our table and we look up the activity coefficient of hydrogen at 0.1 molar, we will see that it is equivalent to 0.83. So what we will do is we say originally that pH is equal to negative log of the H concentration. This time we are going to multiply it by the activity coefficient of H plus. So what this gives us is negative log 0.1 multiplied by 0.8 gives us 1.08 as an answer. So notice our original equation gave us 1. This one gave us 1.08. So the activity has a potential to have a slight effect on the pH of the solution. Keep that in mind. Actually, this is actually written wrong. All right. So I just want you to note that's how we would do it using activity coefficients. I will say though, don't expect to really use them too much for any of this acid-base stuff. We won't really talk too much about activity coefficients too much more besides what we talked about last time. So now let's talk about pH of 0.1 molar KOH. Notice that this is a base. pH equals negative log H concentration. don't have the H concentration. We have the OH concentration. So we need to essentially do something. We know that if we have 0.1 molar KOH, we have 0.1 molar OH. Because we're going to say this is a strong base, therefore we're going to say it essentially goes 100% dissociation. Therefore, its concentration is equal, or its OH concentration is equal to its concentration of the non-dissociated form. However, we have an OH concentration, and our pH formula needs a pH or an H concentration. So we need to essentially do something. We need to note that Kw is equal to the concentration of H multiplied by the concentration of OH. We also need to make note that Kw is equal to 1.0 times 10 to the negative 4. So, if we have the OH concentration, we could use this to determine the H concentration simply by saying Kw divided by OH is equal to H. What we will do now is we will just plug in to this formula. We know that Kw is equal to 1.0 times 10 to the negative 14th. Our OH concentration, well, we have our OH concentration right here, 0.1. 0.1. And at this point, we just need to solve this, and this will give us 1.0 times 10 times 10 to the negative 13 molar H. So now we can say that pH is equal to the negative log of 1.0 times 10 to the negative 13th. And that will be equivalent to 13. This is the basic way that we solve this problem. I'm now going to give an advanced type of problem. We have the solution 1.0 times 10 negative 8 molar. I want to note that this is a very low concentration of KOH. Our KOH calculated, whatever. So let's say I have 1.0 times 10 to the negative 8th molar of KOH. So I have Kw is equal to the OH concentration multiplied by the H concentration. Kw divided by OH is equal to H. So 1.0 times 10 to the negative 8th molar. Whoops, not that. 1.0 times 10 to the negative 14th. Which is Kw all over 1.0 times 10 to the negative 8th. Calculator real quick. Eighth. Eighth. That equals to 1.0 times 10 to the negative 2 H concentrations. And if I take the negative log of this value, see, negative log log of 0, 2, we are going to get 2, which doesn't make sense. So, the issue here is that water itself, the autoionization of water is producing a higher concentration of OH than this OH essentially has in it. So we need to do a multi-step equation here to solve for the actual pH. So this is what's going to happen when we have a super low concentration of an acid base. We need to do what's known as the systemic approach for calculating pH. So this is wrong. It's yield a failed answer. We need to come up with several equations for everything that's going on in solution and then combine them together. So first, we know that H2O will undergo something known as autoionization to form H plus OH. We also know that Kw equal to the concentration of OH multiplied by the concentration of H, which is equal to 1.0 times 10 to the negative. So, at this point, we also know, what else do we know? We know that OH has two sources. So it comes from H2O, autoionization, and from KOH. And that KOH is 1 times 10 to the negative 8th mole. So, say H2O. I already have that written down. I have H2O is OH plus H, and we KOH is equal to OH minus plus A plus error. or OH minus is equal to plus H. Anything else? I think that's everything we need. So we know H2O auto ionizes to H plus OH. We know that constant is 1 times 10 to the negative 14th. So Kw is OH times H for that auto ionization. We know that OH comes from two sources. It comes from that H2O and it comes from that KOH. So we could say that the OH that comes from KOH is equal to OH equals to KH. And we could say that the H that comes from the H2O, so we could say minus from the H2O. We have the formula of this. So say that we don't need to know this. Not required. Therefore. So this therefore so, so what's going on is we have this KOH yielding OH, and we have this H2O yielding OH. That means that all of the OH in the solution is coming from the K and is coming from the H. So if we measure the H concentration and we measure the K concentration, add it together, we have the OH concentration. Because it's coming from the K that we put from the KOH, and it's coming from the H from the H2O. Say that. Each of these are losing an OH. So when they lose, H2O loses an OH, it becomes H, and when KOH loses an OH, it becomes K. So if we know the concentration of K and we know the concentration of H, we know the concentration of OH. And if we know the concentration of OH, we know the concentration of H in solution, and therefore we know the concentration, or the pH rather. So let's put all of these equations together into a single rationale. So if we have, we could say concentration of K equal to the concentration of KOH. And we could say that this is equal to 1.0 times 10 to the 8th, or negative 8th. We know that AW is equal to H equal to 1.0 times 10^15. And we could set h is going to be equal to x. So if we do this, we could rewrite our equations as OH equals K plus x. We could say that KW equals K plus x divided by x. Because OH is K plus x, OH is K plus x, H is x. We could say that KW is equal to KX positive x squared. And we could say that 1.00 times 10 to the negative 14th is equal to 1.0 times 10 negative 8 x plus x squared. So here is our equation where we have our x's. At this point, we could set our equation equivalent to 0. So 0 equals 1.0 times 10 to the negative 8th x plus x squared minus 1.0 times 10 to the negative 4. We arrange this a little bit differently. X squared plus 1.0 times negative 8th x minus 1.0 times 10 to the negative 14th equals 0. You see that we have a quadratic equation. At this point, you just need to solve the quadratic equation by plugging into the quadratic formula, factoring. Numbers probably won't be easy to factor, so the quadratic formula is your way to go. Or if you have a calculator with a CAS system or Wolfram Alpha, it is also able to solve this for you. We will see that we get an x value equal to 9.6 times 10 to the negative 8th molar. This is going to be equal to the concentration of hydrogen. So now if we take pH as equal to the negative log of 9.6 times 10 to the negative 8th molar, we will get pH equals 7.02, which makes sense. So, what is the rule here? What is the takeaway from all of this? So, acid base if the concentration equals 10 to the negative 6 to 10 to the negative 8th, we will use the systematic treatment. So if the acid-base concentration is greater than 10 to the negative 6, pH will equal to the negative log of the concentration of H. And finally, if the acid base concentration is less than 10 to the negative 8th, pH equals 7, because it's at this point it's just so low it doesn't matter. So these are the essential criteria to take away from everything so far. So Ka. Ka is known as the acid dissociation constant. So if we have an acid in the form of HA, is in equilibrium with H plus A, we would say that Ka is equal to concentration of H plus A minus all over concentration A. I want to note here that everything you see here that we've done previously is the case for a strong acid base. Now that we are talking about Ka values, we are talking about weak acid bases. So everything going down, we are specifically speaking about weak acid bases. They need to be handled differently than strong acid bases. So we could say that Kb is equal to the base dissociation, dissociation constant. And we could say that it is equivalent to the base plus H2O is in equilibrium with the salt, the base, plus OH. And likewise, we could say Kb is equivalent to concentration of the salt of the base multiplied by the hydroxide concentration all over the concentration of the base. What else can we take away from this? Also say that we have something called pK value. So pKW is equal to the negative log of the KW. That is equal to 14. We could say that the pKa is equal to negative log of Ka value. And we could say the pKb equal to the negative log of KB value. So as K goes up, pK goes down. So a big K value means a small pK value, and a small pK value means a big K value. So just keep that in mind. This all goes into, what does this mean? Lower pK means higher dissociation. Higher pK means higher K rather means higher. So as the pK value gets lower, we get more of the compound splitting into its parts. As the K value gets higher, we get more of the compounds. So we could say that the Ka multiplied by the Kb is equal Kw for a conjugate pair. What that means is they have to be part of the same acid or part of the same base. So the acid and its salt, or the base and its salt. So what we're going to say here is Ka is equal to H plus times its salt over the acid's concentration. Kb equal to pH, so the base is salt, times the hydroxide concentration. All over the base's concentration. And the Kw is equal to H plus concentration times the OH. So we're going to use all of this to essentially solve our acid-base problems of weak acid base. Let's say that we have a Ka of 1.07 times 10 to the negative third. And we have an H concentration of 0.050 molars. Find pH. This would be your problem. Well, we know that HA reacts with H, reversibly with H plus A minus. So the acid reacts reversibly with hydrogen plus its salt. And we know that H2O is also acting reversibly. Hydrogen plus OH. That's the first point. Second point. We know that all hydrogen comes from H2O and HA. So we know that all the hydrogen that's being released into solution is coming from the acid plus the acids from the water from autoionization. What that means is that H plus is equal to OH plus A. This is from water, acid. However, I want to tell you how we will be handling everything. We know that the concentration of A for any respectable acid is going to far, far, far outweigh the concentration of the autoionization of water. Therefore, we could say that the concentration of H is approximately equal to the concentration of A. So we're going to disregard water's autoionization, and there is a reason why. If we do not disregard the autoionization of water, what we get is an equation that has a third power in it. And as a result, we would have to solve for a third power equation, which is difficult. With the help of technology, it's doable, but for our case, we will leave things in the quadratic equation realm by just making this assumption that the concentration of the H being added to the solution from the acid far outweighs the concentration of H being added to the solution from water's autoionization. And this will be true of all cases of any problem you are given. So, what else can we state? We know that the concentration of the acid initially is equal to the concentration of the salt plus the concentration of the remaining acid in solution. So what does this mean? This means when we put this acid in solution, some of it's going to disassociate into H plus HA, but some of it is going to stay in its HA form. So we could say that the initial concentration of the acid is equal to however much of the salt that is released into solution, plus however much of the acid remains in solution. This is going to help us a little bit in setting up some equations. So we can say that Ka is equal to the concentration of H multiplied by the concentration of A all over the concentration of HA final. So this is going to be the final concentration minus. We know that Kw is equal to H plus and OH minus. So we can have H, since H is what we're searching for, be equal to X. And so Ka will be equal to X. And what is A? Well, what is A? We said that H is equal to A. So it will be X times X all over HA of F. And so what is HA of F? HA of F is right here. So HA of F will be HA of I minus A. So we will say HA initial minus X. This is what our Ka is going to be equal to. And if we simplify this a little bit, we will get X squared over 0.050 minus X equals 1.07 times 10 to the negative 3. So this value, this 1.07 times 10 to the negative 3, we were given at the start. We were also given the initial concentration of the H at the start. So this is the initial concentration of the H or the acid. Oh, I say HA. So when we solve for X, X is equal to H is equal to 6.8 times 10 negative third. And if we take the negative log of 6.8 times 10 to the negative third, we get pH is equal to 2.17. So this would be the pH of this solution right here. And we would essentially use this approach to solve for the pH given a weak acid or a base. What is the takeaway from this? Here is the general formula you can use. Ka is equivalent to X squared over HA initial minus X, or X is equivalent to the H concentration, HA equals initial acid concentration. And this only holds true only if H plus concentration approximately equal to the A concentration. pretty much this means that the acid that you add to solution has to be of a greater concentration than the autoionization of water, or significantly greater. Technically, that will be the only case you're given. So we're going to talk about two more things, and then we'll be done. Let's talk about the handling of a weak base. So let's say that we have the generic base B plus H2O is going to react to form BH plus OH minus. We know that Kb is equivalent to BH, the concentration of BH, times the concentration of OH, all over the concentration of, or the initial concentration of, or the final concentration rather, of the base. So this is the final concentration of the base left in solution. We will assume that BH is equivalent to the OH, so we are going to disregard water's autoionization, and we are going to set OH equal to X. If this is the case, the final concentration of the base is equal to the initial concentration of the base minus the salt. BH So we have the final concentration of the base being equal to the base's initial concentration minus the salt of the base. What we could do is we could rewrite Kb. And Kb could be rewritten as x squared over the initial concentration, or the final concentration of, initial concentration of the base, rather, minus, because we are going to set that BH approximately OH, and so OH is equal to X. Wrote all that. So in the same way that you would be given a acid, you might be given a base, you might be given a concentration of the base, and you might be given a Kb value. You could use that to find essentially the value of X, which would be the concentration of OH, which you could then use to find the concentration of H, which would then give you the pH. So you would do that in the exact same way you would do the last problem, but this is the general formula for solving for bases. The last thing I want to talk about is known as the fraction of dissociation. So the fraction of dissociation from HA would be the concentration of A, or the salt of the acid, all over the concentration of the salt of the acid, plus the final concentration equal to X over X plus H A initial and these two x's cancel out. X minus x is 0. So this is equal to x over HA initial. So if we have the initial concentration of the acid and we divide it by x, which is essentially equal to H, say that X is equivalent to H, which is essentially A. If we take the concentration of A or H and take it over the concentration of the acid, we will essentially determine the dissociation of the hydrogen. So if we use, we have a value for this problem. Let's use this. Let's use the 6.8, which is the hydrogen concentration. So let's use 6.8 times 10 to the negative third all over 0.050. And 0.050 comes from, where does it come from? It comes from the initial acid concentration. So we had initial acid concentration of this, and that gave us a final hydrogen concentration of this. So if we take the hydrogen concentration and divide it by the initial acid concentration, we will get a value of 0.14. 0.14. So this is our dissociation fraction. If we take our dissociation fraction and multiply it by 100, we get our percent dissociation. And what that will give is 0.14 times 100 is equal to 14% dissociation. So 14% of our acid dissociated in our previous problem over here. This exact same process can be used to determine a base dissociation. Instead of using the concentration of hydrogen, we would use the concentration of the base. And instead of using or OH, and instead of the concentration of the acid, we would use the concentration of the base. So it would be OH all over that is essentially all I would like to talk about for today's lecture. This will conclude everything that you need to know on weak and strong monoprotic acid and bases and how to essentially determine the pH and or concentration for them. Take care and until next time.